All right, so you guys are now in charge. Take us away.
All right, thank you. All right, well, hello and welcome, and thank you for coming today. Special thank you to any guests or sponsors that we have. We are the Jammers Pipette team, and thank you for coming to our final presentation. So to introduce our team, we are Ariana Aguilar, Ryan Hostetter, myself, James Monahan, Mohammed Taha, and Sydney Vorberg. Starting out today, I'm going to go through an overview of what we're going to talk about. And that starts off with going over our final product as a whole. Then we're going to break it down into the individual subsystems and mechanisms. Then talk about some of the functional analyses and the failure mitigation that goes with a couple of those. We're going to show you a demonstration of our final product and round it all out with the testing and calibration that got us to where we were. So moving on. On the right, we have a couple pictures of our design. This design features a 3D printed housing and structure made of PETG or PETG with a couple of components inside also made out of the same material, like our drive nut and our tip ejection mechanism. In this design, we're pretty proud to also say that we only have 2 machined parts, cutting down on a lot of our cost, with only one of those machined parts requiring, or only one surface of those machined parts requiring finishing as well. So we've cut down on that time. And this device is for the larger portion of pipettes that can reach 500 to 5,000 microliters, and our max volume is above that 5,000 microliters. This design also features the magnetic PCB board that goes along with every other device, along with a motor that would be on pretty much everyone else's designs today as well. So we would like to point out that our unique component cost is under $10, while the total cost using those same components that other teams would be using is also below $50, with our customer needs being at 100. We're very proud of these numbers. The dimensions are also within the constraints necessary for the gantry and the enclosure system, and our mass is only at 0.69 kilograms. Talking a little bit more about what makes our design special is the smooth and sleek design. When working with and assembling this piece, our rounded edges are very intuitive to use, and the internal components can only be assembled in one way. So we don't have to worry about anyone using this or performing maintenance on this later and reassembling it in the upside down, backwards, wrong orientations. The drive nut only goes in one way, everything only goes in one way. And this all comes together very seamlessly with trapped hex nuts and set inserts exclusively. Everything fits and everything has a very clear location of how this can be fastened together. All of our fasteners also feature hex heads, so we don't have to worry about any Phillips head stripping or anything like that in the future. Moving forward, I'm going to pass you along to James to talk about one of our subsystems.
This is the Pipette mechanism. So as you can see in the movement in the GIF, the drive nut is moving along the lead screw. This also moves the plunger in and out of the nozzle. The linearized movement is due to the shape of the drive nut being a slot, which does not allow it to rotate, forcing the drive nut to move up and down instead. As the plunger is moving in and out of the nozzle, the O-ring is placed at the top opening of the nozzle. This acts as a seal that creates suction to draw the fluid when the plunger is moving up. This also creates pressure to eject fluid when the plunger is moving down. The amount of fluid drawn ejected is based on the movement of the plunger in relation to the O-ring inside the nozzle. For the theoretical volume calculation, the plunger diameter is 11 millimeters. The motor has 4 start lead screws with 2 millimeter pitch each. So what that means is each revolution, it's moving 8 millimeters in vertical displacement. And for each revolution, there were 200 motor steps. In terms of per step, it is 1.8 degrees or 0.04 millimeter in vertical displacement. The volume calculation equation is shown as a result of circular area based on the plunger times the vertical displacement of the motor steps. Next slide, please. That is the ejector mechanism presented by Sydney.
Okay, so here you can see our ejector mechanism. This is made up of an interior ejector piece, which passes through a hole in the base to connect to the lower ejector piece, which sits around the nozzle. The spring allows for the ejector to return into place once pressure is removed from the interior ejector piece. The spring used is actually taken from the manual micropipette we were given as an example at the beginning of the semester. To reduce the cost for the lab, we simply made use of this spring and determined the specifications of it with the intent of finding a spring with the exact specifications at a later point. We determined that the spring constant was approximately 480 newtons per meter, and to compress it, the required 3 millimeters to eject the pipette tip. Our testing showed that it would take about 150 grams of force, or about 1.45 newtons. So our calculations for the motor showed that it could deliver approximately 12.5 newtons of force. So our motor is easily able to apply the required force to cause the tip ejector to be ejected, or sorry, the pipette tip to be ejected. Many of the issues with our initial design were derived from moments created in the interior ejector piece. Therefore, a lot of our efforts went into preventing friction between the interior ejector and the base. In order to prevent a moment being enacted between, or sorry, in order to prevent a moment being enacted on the interior ejector, which might result in the part becoming jammed against the base, you can see our drive nut extends fully over the interior ejector piece. Additionally, to keep the interior ejector in place, you can see extrusions on the outside of the part that align with tracks within the interior housing. And as our ejector mechanism is fully contained within the pipette, there is no need for any additional interference to remove the contaminated pipette tips. And so this GIF shows exactly how the mechanism works. The drive nut moves downward into the interior ejector, which pushes the exterior ejector downwards into the pipette tip, causing it to be forced off. When the drive nut moves back upwards, the ejection mechanism retracts and a new pipette tip can be pressed onto the nozzle. And I'll pass you off to Mohammed.
And here we will talk about the overall evolution of the design process that we had kind of went through. And so initially, as you can see, I'll start off with the interior housing. And if you look at if you compare the two designs, you can clearly see that the housing was greatly increased in size. And the reason why we did this in width, and the reason why we increased the size was to allow for more space for the interior parts to have a little more wiggle room in terms of tolerances and be able to truly fit everything inside. And additionally, if you can tell, it was actually the interior housing is also split into two pieces. It was the upper part and the bottom part. And the reason why we split it into the second piece was to allow for easier assembly and easier access to the internal parts of the inside the housing for our micropipette. And additionally, we also utilized trapped hex nuts instead of the initial heat set inserts that we were using. And we switched to this method because we were having some issues with alignment, and we noticed with the heat set inserts we were kind of leading to wandering, and it was messing up with some of the tolerance values that we were incorporating. So we switched all together to trapped hex nuts. And additionally, going onto the nozzle, as you can see, the nozzle was actually greatly increased in size. And the reason why we had to do this was because the objective that we were provided was we had to fit a micropipette tip within the 500 to 5,000 microliter range. So to accommodate this, we had to make our nozzle much larger. And additionally, as you can see, on top of the nozzle, we actually utilized a hex nut. And that's, if you look at the hex nut, it's actually recessed onto the thick bottom base of the interior housing. And we did this, and then you can see it's also threaded onto the nozzle, the hex nut. And we actually did this because it allowed us to create a lot stronger and more secure hold between the interior housing and the nozzle. And by doing this, we actually also were able in having a better alignment with the plunger. And speaking of the plunger, one thing that we had changed in the plunger, and that's actually different from most groups actually, is we actually incorporated a press fit by creating a knurl on the plunger and having it press fit onto the drive nut. And we did this to kind of ensure ensure a strong hold within the drive nut to ensure there was no sort of like issues with it falling off or anything, and it worked well. And additionally, we also, as Sydney mentioned earlier, we increased the size of the drive nut. And we increased the size of the drive nut so that when it fully clasps down, we are actually able to fully cover the interior part of the tip ejector to avoid the issues of the moments that Sydney was mentioning earlier. And additionally, going into the last part with the ejection mechanism, the first thing we kind of did first was move the kill switch up, and we kind of did that so we have more space to work with. And as you can see, the kill switch is also, sorry, not the kill switch, the spring, there's a spring placed on to the bottom of the onto the bottom of the interior housing part, and it's right above the interior ejector, and it served as like a fail safe between the bottom of the drive nut lead screw. And the way it works is once the drive nut reaches the tip ejector, it pushes the the tip out, and that's when we also created that, which was not initially placed in the design as well. And from here, I'll pass it back to Cindy for failure analysis on the drive nut.
Okay, so due to the forces enacted on the plunger to move it up, or on the drive nut to move the plunger up and down, the drive nut was determined to be the part that was most likely to fail. So when the motor rotates the drive shaft, the drive nut tries to rotate about it with the plunger, but the plunger is held into place by the edge of the nozzle. This fixation prevented the rotation of the drive nut and thus causes it to move vertically. Therefore, with every change in height, the drive nut experiences stress from pushing against the plunger. So to determine the stress, the edge of the drive nut was modeled as a wall with a force acting upon it. The stress was estimated by the force over the minimum cross-sectional area of the drive nut wall. This was approximated to be about 185 kilopascals. The approximate stress was then compared to the yield and tensile stress of the drive nut's material, PETG plastic, to determine the possibility of the drive nut permanently deforming or even breaking. So as you can see, in both cases, our factors of safety were found to be very high, displaying that the drive nut is highly unlikely to break or permanently deform under the stresses caused by the motor.
Now, our O-ring was designed to be placed within the aluminum nozzle, and this is due to the fact that it is easier to get a surface finish on our plunger than it is on the inside of the nozzle. And the importance of the surface finish is that it decreases the wear and fatigue over time, as well as it is important in sealing. So to ensure that the O-ring is properly sealing, we did a pressure analysis that the O-ring faces when in motion. So if it faces when in motion, the O-ring experiences pressure.
Hey, Ariana, can you take a sec? Your audio's kind of cut out.
Audio cut out. It's really quiet.
I don't know if it connected to a headset or something or disconnected.
Can you hear me now? Can you hear now, or is it that?
Yes.
Is that better?
Yep.
Okay, I'm sorry. Okay, did you hear the beginning part of that? Okay, so to ensure that it's properly sealing, we did a pressure analysis. And so in the free body diagrams, you can see that the O-ring experiences pressure from the plunger when it passes through, as well as pressure from the fluid when it's being sucked up. So to make sure that it's properly sealing, we want to have the pressure from the plunger on the O-ring be greater than the pressure of the fluid, so it can be suctioned up and held in the pipette tip. So using the properties of the O-ring, such as the Young's modulus, as well as the strain and the contact area, we were able to determine the pressure on the O-ring to being 0.98 MPa. And then using the properties of the fluid, we were able to determine the pressure of the fluid to be 0.54 MPa or megapascals. And so you can see that the pressure on the O-ring is greater than the pressure of the fluid, ensuring that we have a functional seal.
So here's a quick video that showcases how a pipette works. In the video, you'll notice there was a delay before the fluid was placed under the pipette tip. This was allowed the pipette to siphon in air first. This extra volume of air is to ensure all the fluid are ejected as the plunger fully moves down. Some fluids has tendency to stick on the inside of the pipette tip. After the fluid was ejected into the beaker, the fluid inside the beaker was measured using the scale. This is how data for calibration was collected. For calibration adjustments of the pipette, there were linear error and offset error. Next slide, please. Calibration of linear error. The linear error is derived from the plunger being slightly smaller than 11 millimeters. This resulted in error per motor step. To adjust for this linear error, multiple data points were taken at different number of steps, and the results were plotted against the theoretical data to generate two linear functions that represented the difference in volume per step. The orange line represents the theoretical predictions, and the blue line represents the experimental results. As the number of steps increases, the cumulative error increases in turn. This can be seen in the graph as experimental linear equation moves farther away from the theoretical linear equation as the step increases. To adjust the volume per step, we use 3.6514 as our new volume per step instead of the theoretical. Next slide, please. Calibration offset error. The offset error was caused by the plunger being machined in sections. This resulted in air sections on plunger with slightly larger diameters. The larger diameter resulted in more fluid being drawn up. This can be seen as in the graph as the average error still maintains a linear relation but shifts to the left. To adjust for the offset error, the motor step input calculator based on given target was broken into sections, and the sections were determined based on where the shift occurred on the graph. In the first section, it was from 500 to 1,000 microliters. There was no offset error needed because it was before the first bump. The second section was 1,000 to 3,500 microliters. And the offset error was -3 motor steps. And the last section was 3,500 to 5,000 microliters. The offset error was 11 motor steps. And after all the calibration were done, we were giving a random target value of 1,200 microliters. Our pipette performance resulted in 1,205.6 microliters. The customer required tolerance was ±10 microliters, and our additional 5.6 microliters fell within this range. Next slide, please. Thank you for your time. Please let us know if you have any questions.
All righty, thank you guys. Well done. We'll go ahead, open it up for our sponsors and our panelists to go ahead and weigh in and ask any questions they might have about your presentation.
Yeah, so this is Rick Miles with Northrop Grumman. If you could go back to your start with your first calibration. Yeah, nope, you just had it right there. So looking at this, so when I see theoretical data, I don't think of points. I think of just a line, right? So I was trying to understand what you're trying to say here, the theoretical versus the experimental, because I'd expect experimental to be points and theoretical to be based off an equation, right? And then you would curve fit your experimental data to see how it compares to whatever that equation happens to be. So I was a little thrown off as to what you're trying to show here.
Yeah, Rick, for sure. This graph is exactly what you're saying, that it's based on a curve. We fit points directly on top of what we tested to directly compare those points. So it is, the theoretical is directly from a equation curve, just like you said, but we put it in for the points that we tested just to get a good idea of how off they were.
Okay. And then the trapped hex nuts, if you could go, there was a picture there where y'all walked through your different hex nuts. If you could go to that slide.
Where did you mean?
Yeah,
if you go to my final product slide, I can point stuff out, I believe. Okay, so around the base of that, the central column of the structure, yep, exactly. The way it's fastened is a trapped hex nut. So we've 3D printed a hex feature that's recessed into that. So we just pop a hex nut in there, it sticks there, it stays there forever. And a screw is come from the other side using a tool to fasten that.
Okay, so basically, because one of the customer requirements was like a toolless in order to disassemble, right? So
Yeah.
basically, y'all's one constraint here is you need a hex wrench in order to be able to disassemble a
Yeah, just an Allen wrench.
Allen wrench.
Dudes,
Yeah.
and every single. Oh, sorry, Sydney. I'll let you talk about that.
The gaps that the hex nuts are fit into are hex shaped. So when you twist just the Allen key, the hex nuts stay in place, and so the gaps that they're in essentially act as a wrench holding those hex nuts in place.
Okay.
Yeah, they're not like captive hex nuts. If you're thinking about the ones that are like dual threaded with the outside, they're just regular hex nuts that sit within a recess.
All right. And then could you go to the slide on the O-ring pressure calculations? So I love seeing free bodies, but I've got to say I'm confused as to what you're showing in your free body here. I can't tell looking at the side view you have there of where your O-ring is, and then your free body off to the right as to what lines up with what.
Yeah, so I'll field this one. So the middle picture is just kind of like, so you can see the placement of the O-ring, that it's within the nozzle. And the free body diagram right there is, so you have the pressure from the nozzle when it's being placed, when it's being pushed against the plunger. So you have pressure, a force, like a reaction force from the plunger. So F1 would be like the plunger, and then F2 would be the reaction force. And then the pressure, the PA is the atmospheric pressure, but the pressures that we're finding here are based off gauge pressure. So the pressure from the atmosphere is actually going to be just negligible, 0. And then you have the pressure from the fluid when it's being pushed up.
Okay.
Just to build on it, they're on the same orientation. It's just a cross section of that ring.
Yeah, I guess I'm the way I'm picturing it is that you've got the fluid down below, you got the atmosphere up top. It seems like it would still be like a disc type shape. Maybe I'm just not picturing.
Yeah, so this
exactly.
is just one side of the O-ring. Essentially F2 and F1, those are forces. Yep, thank you, Sydney. They are forces from the compression of the O-ring itself sitting in that groove with the fit that we have created based on the specs for this specific O-ring. Does that make sense?
A little bit better.
Okay.
And then if you could go to where you talk about your plunger press fit on, yeah, the press fit on the plunger. Yeah, so I kind of missed exactly what the advantage was of having that press fit in.
So
Okay, so I got it, or
I can handle, or you can't, Sydney. I was just going to say that essentially we took the concept of the like heat set or cold set inserts and use the same sort of knurled feature on the outside of the top of our plunger to press into this plastic 3D printed drive nut. The reason we chose to do this is it requires less fasteners for this specific component. There's less wiggle room then, and our calibration can be a little bit tighter. Additionally, it cuts down on cost. It's a very simple machining process to add that feature to the top of a cylinder, essentially, and placing this into a easily changeable 3D printed drive nut was our goal.
Right. So I guess what I was going through in my head, one of the other things you talked about was increasing the volume, and you increase the volume, but in order to be able to deal with tolerance issues. So I was trying to picture if we're press fitting that on, where does our issue come in with tolerances?
So when we were first doing some of our testing, we were having problems with the the plunger rotating and moving about in the drive nut. So by press fitting it into there, we make it stick a little bit hard. Well, we keep it completely fixed within it. And then, so we increase the distance, not so much for tolerances, but to make sure that our drive nut actually was able to fit. So our drive nut is extended in length. So we had to increase the size of our interior housing.
Okay, that makes more sense. All right, thanks.
Thank you.
Do we have any, I'm sure we have additional questions. Anybody else got follow-ups? All righty. Well then, we'll go ahead. We're now a minute ahead of schedule, which I'm sure, just as happens with Dr. Traum, I am going to ruin. But congratulations, guys. You're done. You're free, as I like to say. But yeah, congrats for finishing everything out strong. Great presentation. And go ahead and go about the rest of your week in peace.
Yeah, thank you. Thank you, Dr.
Thank
Nimi.
you.
And thank you,
Good job, guys.
Rick Miles, for being here. We appreciate you guys. Thank you.
Thank you.
All righty. And so we are now on presentation slot 18, which Dr. Traum knows which Pipette Group number this is.
Yeah, I'm